All right, we want to talk about the next simple machine. This one's going to be called a pulley, and you've seen these before. There's two types of pulleys. There's called fixed pulleys, and there's movable pulleys. First thing we'll talk about is a fixed pulley. We'll say I have a pulley up here on the ceiling, and I can throw some rope up over this pulley down to a resistance force. Force resistance, and I can apply some effort to this. And how much effort is it going to take? Well, I think you can understand here that it's going to take this exact same amount of effort to pull this down as it is going to be lifted up. So what's the advantage of this? Well, there is no real force advantage. The advantage is that I can just change the direction. So I can be down here pulling down and having this thing go the opposite direction. So that's the only real advantage here. The mechanical advantage, the IMA of this, would be 1. So fixed pulleys, the IMA is 1. That's all it is. So whatever force I'm putting in, I'm still applying the same amount of force. And remember, IMA actually doesn't have to do with forces. It has to do with effort distance over resistance distance. So however far I pull this rope down, the resistance will move the exact same amount the other way. So dE over dR, those distances are going to be the same. The IMA for the fixed pulley is going to be 1. All right, let's look at a movable pulley. So I have a ceiling here, we'll say, still. And let's think here. So I'm going to have a rope coming down here like this. Well, let's do this. Let's change the color. So I have a rope coming down here, and then here's a pulley, a movable pulley, and we'll say that attached to that movable pulley is some resistance force. And the rope comes up here, and maybe I'm right here, and I'm pulling up on this rope. Okay, a movable pulley. When I'm pulling up on this rope, this would be my effort force right here. And so I'm going to pull this rope a certain distance, effort distance, dE. And that means this resistance is going to be moving up a certain distant resistance. And IMA is dE over dR. Now, since this is a movable pulley, it might not be intuitive, but the amount of distance right here that you're pulling this will actually be will be farther than what this pulley or this resistance actually is going up. You're not pulling directly on this resistance. You're pulling through this pulley. So some of this string is going this way, and some of it's going this way. So this resistance isn't going up nearly as far as the amount of string you're pulling through. So the IMA here would be the dE over dR, and dE is going to be bigger than dR. So you're going to get an advantage of greater than 1 here for a movable pulley. In fact, your IMA for a movable pulley is actually going to equal 2. It's going to be 2. You're going to pull this twice as far as this actually is going to be raised up. So the ideal mechanical advantage for a movable pulley is actually 2. And there's other ways to think about this, and sometimes I've heard people say all you have to do to figure out the ideal mechanical advantage is count the number of supporting ropes. So here's a rope going up and here's a rope going up. These 2 ropes are supporting this weight, and there's 2 of them. So your ideal mechanical advantage is 2. But I think maybe the easier way is just count your movable pulleys and take it times 2, and that's always going to be your ideal mechanical advantage of a pulley system. Okay, so we can still figure out work input. If you remember some of these things, work input is the effort force, however much force you're pulling here, times the effort distance. So I could figure out how much force I'm pulling here times the amount of distance that I pull it. And the work output is still resistance force, which is this weight, times how far it's going up. So I can still calculate all these things out the same for all these. Okay, we can take fixed pulleys and movable pulleys and kind of put them together. Normally, when we have a whole bunch of pulleys in a system here, we call it a block and tackle. Block and tackle. So let's say I have like I got like a 2-pulley system here. There we go. That's a fixed pulley, and I should make those pulleys like red. There's a fixed pulley, and then down here I'll have another movable pulley type of a thing with a big weight on here, resistance force. And so the way this could work is I could have let's see, I'd have a rope attached here that comes like around that pulley, around that pulley, around that pulley, around that, and then it comes down here, and let's say I'm pulling on it right there. There we go. That's a block and tackle. So I'm applying an effort force to this, and I'm going to pull this rope. And I'm going to pull it a long ways. I'm going to really pull a lot of rope through this thing, and this resistance force then will slowly move up, because this pulley right here is actually being pulled up. It's moving up, same rate that the resistance force is going up. So I could find the work input, the amount of force that I'm going to pull on it, times however much rope I'm pulling through. Work output would be this resistance force here, times however far up it goes. And I could figure out an ideal mechanical advantage for this. And if you remember, it's the number of supporting ropes. So there's a supporting rope, there's one, and there's one. This rope here is not a supporting rope. It's opposite the distance, the direction the resistance force is going. So that would not count. You need all the ropes, that would be going against the resistance force. And so that would be 4. Ideal mechanical advantage would be 4. Remember that I think the easiest way, though, is count the movable pulleys, which is this one and this one, right? There's another one. And take it times 2. Take all movable pulleys times 2, and that's your ideal mechanical advantage. So I have two movable pulleys times 2, of course, is 4. That'd be my ideal mechanical advantage. What is my actual mechanical advantage? If you remember how to calculate that, it is the resistance force, Fr, so it'd be this weight, divided by how much effort force you actually are putting into the system. So if this was like 100, just to review, if this is 100 Newton force, if this is an ideal pulley, a perfect pulley, the ideal mechanical advantage is 4, then you would expect to only have to pull this rope down with like 25 newtons of force to be able to lift an entire 100 Newton force. But if I actually do this in reality and I figure out how much force it takes to pull this, it probably isn't going to be 25. It might be something more like 30 newtons. I still would want to do it, right? 30 newtons was still great, better, easier than lifting 100 newtons directly. So I'd still want to do this, but the ideal mechanical advantage then would be 100 divided by 30, not 100 divided by 25. It wouldn't be 4. It would be 100 divided by 30, which is like 3.3, right? 3 1/3. So my actual mechanical advantage might be 3 1/3, even though my number of supporting ropes, or my ideal mechanical advantage, is 4. So that's still a good mechanical advantage. It's just I'm not totally getting everything out of this machine that I possibly could. Of course, the efficiency, remember, is the AMA over the IMA. So it'd be like 3.3 divided by 4. 3.3 divided by 4 times 100 would be like 83%. So it's not 100% efficient. It'd be 83% efficient if I was pulling down here with 30 newtons. I just want you to understand these machines are not perfect. They're not ideal. So this ideal mechanical advantage is just a dream. It's not actually ever going to be that. You'd actually have to use the forces to calculate what the actual mechanical advantage is. And then you take your actual mechanical advantage divided by your ideal mechanical advantage, and you can get a efficiency of the machine. And of course, remember you can do that by taking work out over work in also. That's another way to calculate it. Okay, so that's the pulley.